So hello everyone, thank you for coming to my MSc thesis defense. The title of my thesis is Input Space Augmentation for Skin Lesion Segmentation in Dermoscopic Images. We first begin with the clinical motivation for this work. Cancer is the second leading cause of death globally, and of all the forms of cancer, skin cancer is the most prevalent, with an estimated 5 million cases to be diagnosed in the USA in this year alone. A recent WHO report states that the incidence rate of skin cancer has been increasing in the past few decades. However, the early detection and diagnosis of skin cancer are extremely important, with the estimated 5-year survival rate with early detection as high as 99%. Skin lesion diagnosis is difficult. This was shown in a study between dermatologists and non-dermatologists, where it was shown that dermatologists had nearly twice the accuracy of non-dermatologists, where they were able to diagnose 80% of the cases correctly as compared to 40%. However, the number of dermatologists has been on the decline recently, and there are studies which show that we face an undersupply. And a more recent study showed that the ratio of dermatologists to population is projected to decrease over time. In this thesis, we propose methods for computer-aided diagnosis of skin lesions. Computer-aided diagnosis methods have certain advantages, such as quick, robust, and reproducible results at a reduced diagnostic cost, as well as the possibility of making dermatological expertise available in remote communities through teledermatology. Next, we'll look at how skin lesions are imaged. The first type is clinical images, which are relatively easy to acquire. They have typically no control over the imaging equipment, the field of view, or the illumination condition. The other type, dermoscopic images, sort of address all these problems. They are acquired using a special acquisition device known as a dermatoscope, and they provide a standardized illumination condition and a controlled field of view. Here is a sample clinical image and the corresponding dermoscopic image. You can see that certain features are clearly visible in dermoscopic images that are not visible in clinical images. We look at the problem of skin lesion segmentation. It's an important problem because it's often the first step in the clinical diagnosis pipeline, because localizing the lesion is important. Plus, the segmentation results also provide an added sense of trust in the outputs of automated algorithms. Moreover, some algorithms use segmentation as as guidance to extract features. For example, a recent work by a lab mate of mine, Niki, used skin lesion segmentation masks to attend to certain regions of the image to make a diagnosis, which made it in turn an interpretable diagnosis. Skin lesion segmentation, however, is difficult, mainly because of the tedious and time-consuming process of the manual annotation. This is compounded by the high variance in the appearance of skin lesions, be it in terms of contrast, blur, illumination, or the presence of artifacts. You can see that in this 8 by 8 grid of skin lesion images that they exhibit a huge degree of variance. Finally, another source is the poor inter-annotator agreement in segmentation masks. This is mainly because of the different levels of expertise of the people who annotate, as well as the choice of the tools used, such as polygon-based tracing, flood fill algorithms, or manual delineation. Standardized datasets are important because they make benchmarking and comparing various methods reliable. In this thesis, we use 5 datasets, the ISIC challenge datasets from 2016 through 2018, the DermoFit dataset, and the PH2 dataset. The number of images in each of them are shown here. Since the ISIC datasets all come from the same source, that is the ISIC archive, there is some overlap between them, and this Venn diagram shows the amount of overlap between the 3 datasets. As we present in our thesis, a brief literature survey of skin lesion segmentation using deep learning, we show that most of the work has focused around 3 major areas, that is architectural improvements of deep neural networks, new loss functions, and ensemble methods. However, in this thesis, we focus on the input space of deep segmentation models. In particular, we make contributions towards augmenting the input space using skin lesion synthesis, as well as color channels and illumination-based transformations. For both the contributions in this thesis, we use this unit architecture for evaluating the methods. The unit architecture consists of an encoder-decoder architecture with skip connections, and the evaluation metrics are the same as used by the ISIC challenges, that is pixel-wise accuracy, sensitivity, specificity, and the two overlap-based measures, the dice coefficient and the Jacquard index. Our first contribution is mask-constrained adversarial skin lesion image synthesis. This was published in Mikai Sashimi last year. Here we look at the problem of data augmentation and deep learning. It is fairly well known that deep neural networks rely on large amounts of data to yield acceptable results. An ICCV 2017 paper showed this by training on up to 300 million images, and the validation performance on the Pascal VOC 2012 dataset was logarithmic with the number of images used. And they concluded that there is a logarithmic relationship between here, the performance metric being the mean IOU versus the number of images. Similar conclusions have been arrived at from other works which show that data augmentation is a worthwhile pursuit. There have been several works which use GAN-based augmentation for medical imaging, such as this work which converted cardiac CT images to MR images for segmentation of the left ventricle, or generating liver lesions in CT scans for classification, or generating chest X-ray images for detecting cardiovascular abnormalities. Similarly, there have been several works which use GANs to synthesize skin lesion images, such as progressive growing of GANs, Pix2Pix HD, and DC GAN. However, most of this work cannot be used to augment segmentation datasets, primarily because these synthesized images do not come with their annotations. So the goal here is to develop an approach which can generate synthetic skin lesion images as well as their corresponding annotations. So we propose the solution of master lesion, which is a conditional GAN-based skin lesion synthesis approach. The inspiration for this work came from image-to-image translation, particularly the Pix2Pix paper, which was widely popular and showed that it is possible to construct realistic images of things like cats or shoes from just hand-drawn sketches of their boundaries. We present a very brief primer on GANs. A GAN consists of two blocks, a generator and a discriminator. A generator takes input and produces an output, and it's tasked with generating a realistic image. A discriminator, on the other hand, takes an image as the input and classifies that image as being real or fake. And these two blocks are trained in an adversarial manner. Here's the master lesion architecture. Let's go through this one block at a time. First, we look at the generator. The generator consists of a unit-based encoder-decoder architecture with skip connections. The input to the generator is a single-channel skin lesion segmentation mask, and it produces RGB image of a skin lesion. And here are the blocks for the encoder and the decoder. The discriminator is based on the patch can architecture, and it takes as input a concatenated volume of the skin lesion image and the segmentation mask, and it predicts whether a patch from that volume is real or fake. And here is the patch can block. Next, we look at loss functions used. The generator loss consists of a weighted L1 reconstruction loss and an L2 loss to fool the discriminator. The discriminator loss consists of an L2 loss to detect fake images and real images. We trained the master lesion algorithm on the ISIC 2017 dataset, and here are some of the outputs. We first feed in as input masks from the original dataset, and we observe that no matter how smooth or rough the input mask boundaries are, the outputs always correspond to the exact boundaries. Next, we used polygons and geometric shapes such as ovals and circles, shapes which are unlikely to occur in the real world and potentially unrealistic lesion shapes. But we see that the skin lesions generated are still within the exact boundary as the input masks. Next, we drew two hand-drawn shapes, a blob and a star shape, and deformed them using elastic deformations. And we observed the same pattern, that no matter how strange the shape, the skin lesions corresponded to the input boundaries. And finally, we performed PCA-based interpolation along the first and the third principal components of the skin lesion segmentation masks to capture the change in the size as well as the orientation. And again, observe that no matter how big or small or which orientation the skin lesion masks are, the outputs always correspond to the input masks. To evaluate master lesion as an augmentation strategy, we trained 4 models on the ISIC 2017 dataset with various possible combinations of augmentation choices. The first model used no augmentation and was called no-aug. The second used geometric transformations such as rotation and flipping only and was called classic aug. The third used master lesion based augmentation only and was called master lesion aug. And the fourth used both forms of augmentation and was called all aug. And all the results are reported on the ISIC 2017 test dataset. Here are the quantitative results for them. Of particular interest to us are classic aug, which is the usual way deep learning models are trained, and all aug, which is essentially obtained by adding GAN-based synthesized images to classic aug. We see that the performance number indicate there is a considerable performance improvement by using GAN-based augmentation. We see this in the qualitative results as well. The third row corresponds to the classic aug output and the fourth row corresponds to the all aug output. And we see that in the classic aug outputs, we have a large number of false negative and false positive predictions, as can be shown by the green and the yellow boxes here. Next, we wanted to evaluate the possibility of using master lesion to augment scenarios where we have limited real data. So for this, we chose the DermoFit dataset and we trained 5 models on it. The first was trained using only the DermoFit training data, and the other 4 were trained using varying proportions of the DermoFit training data augmented with master lesion outputs. An important thing to note here is that the DermoFit dataset comes from an entirely different source as the one used to train master lesion, that was the ISIC archive. So here are the quantitative results. As we expected, increasing the amount of training data leads to almost monotonous increase in the performance, as we see along the Dice and Jacquard rows. But what's of particular interest here are the first 2 rows. We see that a model trained with only 25% of the original data, but augmented with master lesion outputs, is able to outperform a model which was trained with the entire original training data, but had no augmentation to train. We see this in the qualitative results as well. The third and the fourth column show the same set of results, and we see that using only 1/4 of the original data but augmenting with synthesized outputs leads to better qualitative segmentation outputs. So to summarize this work, we propose master lesion, a conditional GAN-based skin lesion synthesis approach, which uses skin lesion masks as inputs and generates realistic images of skin lesions as output. And we showed that these outputs conform to the input mask boundaries. And our experiment showed that the output can be successfully used to augment skin lesion segmentation datasets. Our next contribution is on color channels and illumination-based transformations. This was recently published at CVPR ISIC. The main motivation for this work was that deep learning-based segmentation models usually ignore information about illumination or color imaging, an area which has previously been explored in the past. This ISIC paper said that depending on the acquisition setup, the images of the skin lesions can look vastly different, as can be seen in the set of images. The first row shows 2 lesions with melanoma, and the second row shows 2 lesions with benign conditions. And we see that depending on how they were imaged, they can look vastly different in terms of appearance. However, very few works have leveraged information from illumination or color in a deep learning setting, most notable of which are this SPIE-MI paper, which used color constancy algorithms to improve skin lesion classification, and the winner of the ISIC 2017 segmentation challenge, which used the HSV and the CIE lab color space to improve the skin lesion segmentation performance. So our goal here is to incorporate information about illumination and color imaging in a deep learning based segmentation model. We first begin by selecting certain color channels to include. This JBHI paper showed that the normalized RGB color space eliminates the effect of uneven illumination as well as shading based artifacts. So we select 2 channels, the R dash and the V star, which correspond to the red channel from the normalized RGB and the complement of the value channel from HSV color space. They can be calculated like this. And this, it's the complement of the value channel, but to obtain the value channel, we don't need to convert the entire image from RGB to HSV. It can directly be estimated using this formula, where M denotes the maximum number of gray levels in the image, which is 255 for an 8-bit color image. For three skin lesion images, they're RGB images, and here are their R dashed and V star outputs. Next, we want to address the problem of shadows in skin lesion images, because the presence of shadows in images can cause automated segmentation algorithms to degrade in performance. And the goal here is to find an illumination invariant image, also known as an intrinsic image, which is dependent only upon the reflectance properties of the scene being here the skin lesion. So this is how intrinsic images are found using camera calibration. You have a color checker, you image it under multiple illuminants, and when you plot their 2D log chromaticity plots, this is how it looks. For example, for 7 patches from this color checker, green, yellow, white, black, purple, orange, and red, imaged under 10 different illuminants, this is how their 2D log chromaticity plot looks like. And then you find the invariant direction. However, this process is camera dependent, and ideally we would want to find a way to calculate the invariant direction without imaging the scene, which is again the skin lesion in our case, under more than one illuminant. And if we look at this plot, we see that the invariant direction can be found by the direction of the minimum entropy. So here's an overview of this approach. This was taken from a paper published in ECCV 2004. We have an RGB image. We calculate its 2D log chromaticity, and we calculate the entropy for all angles from 0 to 180 degrees. When we look at the entropy values, we find the angle which corresponds to the minimum entropy, and we project the image along that angle to obtain the intrinsic image for the corresponding RGB image. So for the same set of 3 skin lesions, we denote the intrinsic images by intrinsic, and here are the outputs. We see, for example, for the first lesion on the right side, there is an uneven illumination that has sort of been addressed using this intrinsic output. Next, we wanted to obtain a grayscale representation of skin lesions, which is based on the biological and optical properties of human skin, as well as the physics of image formation. So for this, we look at the optical density space, which is denoted by minus log R, minus log G, and minus log B. And a 1999 paper showed that the RGB value triplets for a skin lesion image in the optical density space, all the pixels, all the value triplets lie on a plane. In fact, a 2012 paper even showed that even though the value triplets lie on a plane, most of the data is distributed along a single vector, as we see in this next slide. For example, for this RGB image of a skin lesion, this is the optical density space representation. The axes are minus log R, minus log G, and minus log B. And we see that most of the data is distributed along one plane. And in fact, the entire plane is spanned by this first eigenvector, which can be found using PCA. And in fact, when we perform PCA on this, we see that 98.3% of the total variance is explained by just the first principal component. So the grayscale images of skin lesions are denoted by gray, and here are the outputs for these 3 skin lesion images. And finally, we wanted to look at the problem of shading attenuation in skin lesion images. Shading can often be induced when we image non-flat regions of a skin lesion, particularly areas such as the lesion can be bumpy and not flat. And this can degrade the output of the segmentation algorithms. So the idea here is to normalize the illumination with respect to the intrinsic image. And the illumination can be found using the value channel from the HSV color space representation. So here's an overview of the method. If we have a RGB image of a skin lesion, we convert it to HSV color space, and here is the V channel, the value channel from the HSV color space. Next, we take the RGB image and find its intrinsic image using the first algorithm described previously. And now we match the histogram of the value channel, to the intrinsic image to obtain a shadow attenuated value channel, which we then plug back into the HSV image. And when we convert it back to the RGB color space, we have the shadow attenuated RGB color space representation of the original skin lesion image. So for the same set of 3 skin lesions, we denote SA denotes shading attenuated images. And here are the 3 outputs. Here are some more outputs for 5 more skin lesion images. So here's an overview of the method. We have a RGB image of a skin lesion. We compute all the transformations. Then we take all this and stack them to concatenate them channel-wise. This, along with the segmentation masks, comprises of our new training data, which we then use to train segmentation models. To evaluate the contribution of each of these transformations to improve the segmentation performance, we perform an ablation study on the ISIC 2017 dataset where we train 7 models. The first is the usual using RGB images only. The second takes all the 5 transformation outputs and stacks them column-wise to the RGB image, and we denote this as all channels. For the other 5 models, we drop one transformation at a time, denoted by no dash, where dash is the channel is the transformation output being dropped, to see how much each transformation contributes to improving the segmentation performance. Here, the quantitative results. We see that using all the transformation channels improves the segmentation performance compared to RGB images only by quite a margin. There's a considerable improvement. Next, we look at what performance degradations would happen when we drop some channels. For R dash and V star, we see that the performance drop is minimal when these channels are not included. And this can be explained by the fact that these are fairly easy transformations for the network to learn. On the other hand, dropping the intrinsic channel leads to the largest degradation in segmentation performance, indicating that it's quite difficult for the network to learn the intrinsic transformation. We see the same pattern in the qualitative results as well. We see that when we drop the intrinsic channel, the segmentation performance is visibly affected as there are introduced false positive and false negative predictions all over the place. To summarize, in this work, we incorporated information from illumination and color imaging in a deep learning based segmentation model. And we showed that including this information improves the segmentation performance. And our experiments show the relative value of each of these transformations in improving the segmentation performance. Here are some limitations of our work. For the first work, we saw that our algorithm can generate skin lesion images which conform to the input mask boundaries. However, we cannot yet synthesize images of a desired disease label. So the next step would be to use diagnosis class information as an auxiliary input to the mask to lesion algorithm. For the second work, we saw that incorporating illumination-based information in a deep learning setting helps improve the segmentation performance, but it was unclear why the deep models could not learn these channels themselves. So the next step would be to attempt to learn to estimate or generate this transformation outputs in a end-to-end deep learning setting. We would also like to point out the inconsistent quality of skin lesion segmentation masks, especially in the ISIC datasets, which come from the ISIC archive. The ISIC archive for some images has multiple annotations for the same skin lesion. For example, for these 4, we see that there are 2 sets of annotations denoted by expert and novice. And as we show here, that the novice the expert is not necessarily always better than novice, and this ends up penalizing our models, because in the challenge datasets, whenever there are more than one, they always include the expert annotations. As we see here in the second grid, for these 4 skin lesions, these are the corresponding ground truth masks included in the challenge dataset. And method 1 and method 2 correspond to outputs of 2 of our proposed methods. If we look at the outputs of method 1 and method 2, we see that they fairly accurately delineate the exact lesion boundaries, but because of the excessively smooth or rough, depending on the lesion, excessively smooth or rough ground truth masks, which are not necessarily always accurate, our model ends up being penalized wrongly. So here are the 2 papers used for this thesis, the Mikai Sashimi paper and the CUPR ISIC paper. Here are the papers I excluded from this thesis and references. And thanks a lot to my examining committee, Professor Hamarne, Professor Drew, Professor Avila, and Professor Chang, and to all members of the Medical Image Analysis Lab for all your help and support, and to all the funding agencies. Thank you.